Alrighty, now we just introduced confidence intervals, but now we're going to look at the second type of inference, which is going to be called significance testing. And in confidence intervals, we're trying to estimate the parameter, but now we're going to obtain a sample and see how significant is our sample. Was our sample likely to occur based on the claim, or is our sample not likely to occur based on the claim? So is it expected? Is it not expected? Otherwise, what we call statistical significance. Now, the formal procedure for this is when we're going to look at a claim, otherwise called the null hypothesis, and it's going to get the symbol here, the HO. And the claim is a statement about the parameter. We express the results in terms of a probability that measures how well the data and the claim agree. Now, what we're testing for is called the null hypothesis, and this is designed to assess the strength of evidence against the null. So this is basically saying that the null is our initial claim. This is, there is no difference, there is no effect, there is no change from the historical value. We believe that the null hypothesis is that the true proportion of people who blah, 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 blah is this number. So that's the claim. Now, I'm going to take a sample, and based on my sample, or based on the question that I'm trying to answer, I'm going to look for evidence for the alternative hypothesis, or the alternate hypothesis. And this one here is actually going to get the symbol HA. So we have the ho and the ha. Well, from here, the alternative usually is a statement that there is an effect, there is a difference, or there is some change. So we'll find some evidence by how likely our sample is to occur just by chance alone. Now, we're going to use a template every time we do this. We're going to define the parameter. So P if we're using proportions, and mu if we're using means. So we're going to say let P equal the true proportion of blah, 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 blah. Let mu equal the true mean of blah, 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 blah. Similar to what we've done in confidence intervals so far. Now, our null hypothesis, the HO, is going to be the parameter equals blank. This is the initial claim. This is usually given to us in the problem. Now, the ha is what we're looking for, and we'll say that the parameter is less than, is greater than, or does not equal the claim. And we're going to specify our alpha level, right? Our level of significance here. Now, we're going to use 0.05 unless it's specifically stated. Just like when we use a confidence interval, we use a 95% confidence interval unless specifically stated. So let's take a look here. It looks as though the medical research team has been given the task of evaluating a new laser treatment for certain types of tumors, and the current standard treatment is considered reasonable and safe by the medical community because it has no major side effects and it has a known success rate of 85%. Research efforts are directed towards determining whether the new treatment is less effective than the current standard treatment, and let us define the parameter of interest and state the hypothesis that should be tested. So I'm going to let P equal the true proportion success rate of the treatment. And yes, I see this 85%, but usually when I see proportions, rates, fractions, a number between 0 and 1, that's going to indicate that it's categorical data, our success rate. What was the success versus the failure rate? Because I can't really take the average success, but I can see how successful it was in the study. So once P does that, the claim is that there's an 85% success rate. So I'm going to say that the null hypothesis is that P equals 0.85. The true proportion success rate of the treatment is 85%. Now, we want to see if the new treatment is less effective than the standard. So if the standard is 85% and I want to test that it's less than, the evidence I'm looking for is that the true proportion success rate of the treatment is less than 85%. So there we've defined our parameter and we've stated what we're going to be testing for. Now, I was not given an alpha level, so the last thing I would do here is say with alpha equal to 0.05. And so this little fish looking thing is alpha, basically the Greek letter A. All right, so that's the idea here. We're going to look at textual evidence, we're going to state the claim, and then the alternative is going to be about what we're looking for. So in the claim here, it's always going to be your equal statement. It always is, this is what we believe is true, but my alternative is based on what I'm looking for, based on the sample I've obtained, this is what I think is true, or this is evidence that I'm trying to find. All right, so I'll give you the parameter here, but go ahead and pause the video and try figuring out what the set of hypotheses would be for this situation. Now wait, Mr. Pinto, it didn't give us a proportion. Well, we're just going to assume 50%. And the reason being, thinking back to our properties of confidence intervals lesson, when we don't know the claim proportion, we just say 50% because a majority of people would be greater than 50%. And so that 50% is just a reasonable estimate, right? Could happen, could not happen, 50-50. There's some indifference. But if it's greater than 50%, we would know that that would be the majority. So this should be your answer here. And again, with alpha equal to 0.05. Now, how do we determine if our sample results are significant? And what I want you to think about here is when you go to the carnival or the rodeo and you play a game, you are expecting to lose, right? If you lose, that's nothing special. There's nothing to brag about there. Like, we expected you to lose because of how the games occur. So when you win, we're a little bit shocked. We think, okay, did you cheat? Did something happen? Are you just that good? So what we're doing here is we're looking, is our sample expected to occur? Like, is there anything special about it? Or is it actually very unlikely to happen by chance alone, which would lead to this result being statistically significant? So we're going to look here, and we're going to introduce some new phrases into our vocabulary. Now, the p-value of the test is the probability that we would get the sample result, or one more extreme if the null hypothesis is true. Because remember, we're basing everything off of a normal model here. So if this is the true proportion, I'm saying I get my sample of p hat like somewhere over here. I'm wondering, what's the probability that my sample were to occur, assuming this claim is true? Very much like our sampling distributions. Now, the smaller the p-value, the stronger the evidence that the null hypothesis can be rejected. And the reason being, it's because if it's very unlikely to occur by chance alone, that would indicate that something special is going on here. So here are our two key phrases. We are going to say, if the p is low, and low meaning less than or equal to the alpha level, we reject the hope. And so here, we'll call it statistically significant. So we reject the O, and there is statistical significance against the null hypothesis. Now, if the p is high, such that it's greater than alpha, we do not have significant evidence against the null hypothesis, since our results are very likely to occur by chance alone. There's nothing special here. Now, in general, alpha will be provided, but if not, we'll just use alpha equals 0.05. Sorry about that, y'all. Now, here's how we're going to interpret it. Assuming the null hypothesis is true, assuming that the true proportion success rate is this, the probability of obtaining our sample or test statistic or a more extreme is this. And the one thing I'm going to add here, comma, by chance alone. So that's one edit that I need you to make for me. Now, what does this look like? Let's take a look here. It could look like one of the following, and we have different types of scenarios here. So there's nowhere I can put my face. Sorry, I'll just move it. Now, a one-tailed test is if we are trying to test, and all of these here are for the alternative hypothesis. We're saying that it's less than this value, so I would find my test statistic and find the probability of the sample using a less than inequality, or it's a greater than, and I find my test statistic and find the probability of my sample being greater than that value. So these are called one-tails because notice only one side of the distribution is shaded. And this is our theoretical sampling distribution. Again, assuming that the claim is true. Now, when it becomes two-tail is we're just indicating that there's a difference. I don't know if that difference is positive. I don't know if that difference is negative. I'm just saying that there is some difference here. It just is not equal to the claim. Something's happening. Now, this says 2 times the p-value, because you'll notice that the p-value is just this one shaded region. But if it's a two-tail, you're going to have twice that shaded region because of the symmetry of the sampling distribution. Now, we're not going to focus too much on this today. We're going to look a little bit more into that in the next lesson when we actually start conducting a significance test. So we've got the following here. A recent study on the relative age and effect of career success, blah, 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 suggests that people born in June and July are underrepresented in the population of corporate CEOs. This is consistent with the relative age effect due to school admissions grouping together children with age differences up to 1 year, right? If your birthday's not in June or July or August, you have to wait till the next school year to get in. Well, we believe that this leads to a disadvantage since they're going to be younger than their classmates born in other months. Now, in the sample of 375 corporate CEOs, only 45 or 12% were born in June and July. Is this convincing evidence that the true proportion, P, of all corporate CEOs born in June and July is smaller than 2/12? All right, so let's write the hypothesis test and obtain, we ran the hypothesis test and we ran a p-value of 0.0008. Interpret this value. Would we reject or fail to reject? So notice the key lingo there. We reject it if there's evidence against it, but we fail to reject it if we just do not have enough evidence. And it's kind of like claims court here. You either are innocent, you are guilty, or you are not guilty. And we're going to focus on the guilty and not guilty, because guilty means there's enough evidence to convict you. Not guilty means there's not enough evidence to convict you. And innocent means there's evidence to prove you didn't do it, but we don't really know the truth, so we're going to skip out on innocence. We're going to focus on guilty, not guilty. Do I have enough evidence to reject the claim, or do I not have enough evidence to reject the claim? So here, I would say that the null hypothesis is that P, again, is going to be equal to 2/12. And I am testing that it is less than this, so the alternative, is going to be less than 2/12. And I'll use an alpha level of 0.05 here. All right, so we look. Now, to interpret the p-value, we're going to say, assuming that the true proportion of all CEOs born in June and July is 2/12, so that's the claim. The probability of obtaining our sample proportion or more extreme is 0.008. And then, of course, the last thing I would add here is by chance alone. So it's very unlikely that this is to occur by chance alone, which means that I can probably reject this claim here. And there might be some evidence that it actually is smaller than 2/12, as we saw here, is about 12%. Now, since our p-value is less than the alpha value, we reject the null hypothesis, and we have sufficient evidence that the true proportion of all corporate CEOs might be smaller than 2/12. Now, this is just based on the one sample that we took. So I could take a completely different sample and get completely different results, but in this one setting, I would have enough evidence to believe that I can reject the claim, and it's actually less than 2/12. So that's the template there. You're not always going to have to interpret p-value, but it's a new sentence stem we're going to add to our collection here. Now, what I would like for you all to do is just follow along with me here. Now, let's read the problem. Students in a statistics class like to investigate if more than 2/3 of the Earth is water. To answer this question, students toss an inflatable globe back and forth, and after each catch, a student recorded whether the tip of their pointer finger on their right hand was on water or on land. In 50 tosses, the finger was on the water 38 times. Assuming the conditions have been met, do we have statistical evidence that more than 2/3 is water? All right, so first thing, we're looking for N and P. N looks like 50, and nothing about P, so I have to convert my proportion here. Well, of those 50, 38 of those were successes, so my sample proportion here is 0.76. Now, the initial claim is that there are 2/3 of Earth is covered in water, but we're testing that more than 2/3 is covered in water. So this is what's happening here. Well, 2/3 is about 0.67, so if I were to construct my sampling distribution, the mean would be 2/3, and the standard deviation of the parameter would be about 0.0665, of the statistic. So we've got a sampling distribution here, so I want to find the probability that my sample proportion is greater than 2/3, and I would do this by just treating this like a sampling distribution problem. So I'm going to find the z-score. I'm going to standardize it using the parameters that we've determined. I'll get a z-score of 1.35. And since this is a greater than problem, I'm going to do 1 minus. I'm going to use the complement rule. I'm going to get a p-value of about 0.08. Now, my initial alpha value is 0.05. So there's about an 8% chance that my results were likely to occur by chance. While that's not a significant amount, it's very likely. It's at least higher than 5%. So it wouldn't be too special if this happens, if more than 2/3 of my trials were in water. So our p-value is 0.08, so it could be B or D. And do we have convincing evidence? So yes or no? No, we don't have convincing evidence because our p-value is greater than the significant value, the level of significance here, which means that it's very likely by chance alone that we were to get these results. There's nothing special about my results here. So that's kind of the background of what hypothesis testing is. You're going to look at how likely your sample is to occur, we'll evaluate the claim, we'll state the claim, and then we'll interpret the probability of obtaining our p-value. So in the next lesson, we're actually going to set up and conduct a hypothesis test, so stay tuned.